So speed. By relating distance and time, we can determine speed. Where am I, Mr. Dewick? I want to make sure I get, yep. Which is the distance an object travels. We called that change a delta D, that's how far, divided by the time interval, delta T. If I wanted to give this to you as an equation, I would say this. In English, we call it speed. Now, we don't want to write out the word speed, so we're going to use a symbol. We don't use S because actually what we're really interested in is velocity, and speed is the scalar of velocity, so we're often going to write a V without the vector symbol. Ty, that's velocity, that's speed. Velocity, speed. And it's distance over time. If I want to write it as an equation, what was the triangle again? It was the Greek letter delta. What did that triangle mean again? Do you remember? Change in, which means final minus initial. Emily, that's a good enough question. Let's write it here. Means change in. And to calculate it, Emily, it's always whatever your final value is minus whatever your initial value is. Whatever your ending point is minus whatever your starting point is. But in physics, we use F for final and I for initial, starting and finish. Now we're going to get a bit more specific, and this I didn't do with you last time, Miller. We're going to start to categorize different types of speeds. We're continuing from last day. We have the average, oh, that's spelled wrong, Mr. Dewick, you're missing an A, nice try. The average speed of an object is the total distance the object traveled divided by the total time taken. Okay. Let me give you an example. Every summer, I travel to 100 Mile House. My parents have a little trailer there, and they bring up the grandkids, and then I travel up, and Uncle Kelvin takes the grandkids back. It's about 400 kilometers, and it takes me about 5 hours. What's my average speed? Well, if I wanted to calculate my average speed, I would say the distance that I'm traveling is 400 kilometers. The time is 5 hours. Speed is distance divided by time. What's my distance? Divided by, what's my time? What's that work out to? Now, that's my average speed. I'm willing to bet if you were to look at my speedometer the entire time, rarely am I ever exactly 80. Because in real traveling, just as on the road, you speed up and you slow down. It depends on traffic. And especially if you go out to the interior, you also have hills and things. When you get to the hills, if you're behind a big semi-truck, it's slowing down. And if you get ahead of the game, it's speeding up. 400 divided by 5? No, that's a 5. That's, by the way, that's why we don't use S for a symbol, because it looks like a 5. It's S for seconds, but I'll never use it as a variable. Yeah, don't feel bad. My handwriting, believe it or not, Emily, has improved since when I first started teaching. There. That 80 would be an average speed. In fact, you know what? Probably sometimes when I was going downhill, I was probably doing 100, because that's the speed limit on the Trans-Canada. Probably sometimes when I was going uphill, especially if I'm trapped behind a semi, I'm doing 30. But average speed. Is that okay? You can see, Justine, to figure it out, I said, well, what's my total distance? I traveled 400 kilometers. What's my total time? 5 hours. Oh, and on the way back, my average speed is slower because I'm traveling with 2 kids. And every hour or so, we got to stop. Right? Yep. I'm the cool uncle. That's average speed. Then, Hayden, there's something called instantaneous speed. That's the specific speed of an object at a particular time in time. I don't want the word time in time. At a particular instant. That's the word I want there. Instant in time. That's what I was thinking. What would my instantaneous speed be, Amber, on that trip whenever I glanced at my speedometer? If it said 83, that's my instantaneous speed right then. And 40 seconds later, it might say 78 because I had to tap on the brakes. That's my instantaneous speed right then. Instantaneous speed is usually pretty tough to get if you have a changing speed. And so what we deal with mostly in Physics 11 is what we call uniform motion. And uniform motion says either your speed isn't changing at all, call it a constant speed, or if you're accelerating perfectly smoothly so that we can predict where you'll be at any one time. Not really accurate in real life, but close. But close. So, for example, as I mentioned, a car speedometer reads instantaneous speed. That tells you how fast you're traveling at that moment. Maps usually give you average speed. If you're doing a long trip and you're trying to do the rough math in your head, you're assuming that you'll be starting and stopping, and you're not trying to calculate every stop sign and red light. You don't bother. Then, for an object traveling at a constant speed, what's a constant speed? You're right, Josh. What? Now, we have a fancy word for that. That's called uniform motion. In physics, the word uniform means stays the same. If your speed is never changing, how would your average speed and your instantaneous speed compare? Think about it. Ooh, that was quick. What? Average speed is equal to the instantaneous, that's a hard word to spell, speed. There are some situations where the speed isn't changing, where you can say the average and the instantaneous are the same. We're going to look at one in just a second. Turn the page. So here's our summary. Distance and displacement are similar, but not identical. Which one is a scalar? Who remembers? Distance or displacement? Which one is a scalar, has magnitude only? Distance. This example that I did with you here, I gave you a distance because I didn't tell you what direction 100 Mile House was from Pitt Meadows, Maple Ridge. Magnitude only. Displacement is a vector quantity. It has magnitude and direction. And we said that the displacement of an object is its change in position. Oh. Speed and velocity are also similar, but not identical. Which one, speed or velocity, is a scalar? Speed. Which one is a vector? That's the only one that works for, but it does work for that one. No, we didn't plan it that way, but you can use it.
Is there a nerdy way that we could show that?
I've never come up with it. We just flog it to death so much in Physics 11 that my kids just memorize it the same way that you guys memorize the word the. Like, it's, how do you spell the? You've done it so often. So I've never bothered. I may come up with a way in Science 10. I don't know. And, a scalar quantity has magnitude only. Velocity is a vector quantity. It has magnitude and direction. Velocity is the rate of change of displacement. Say what? So speed is distance over time. Velocity, same symbol but with a vector, is displacement over time. Same symbol but with a vector. Now, at first, Hannah, it's confusing keeping track of the symbols. I will say, though, Emily, if you wrap your brain around it, it's great shortcuts. Yeah, there's no denying the physics notation, vector, non-vector. It's not the easiest to learn, but when you get the hang of it, it conveys so much information with a half arrow instead of having to write out a bunch of instructions. Yeah.
Is it acceptable to write out the word form too?
You can. If you take Physics 11 next year, I'll probably glare at you and damage your self-esteem in a nice, loving teacher kind of a way.
Allowed. It's just frowned upon.
Well, but it's unnecessary, and I'd put up with it this year. I'd accept it this year. It's just you won't see it that way on the provincial, which is multiple choice. So I guess my answer would be try and get used to the symbols, because if you get used to writing them, you'll probably spot them when they show up on a test, he says. Let's apply this. Lesson part 2. Graphs.
And we're live.
Imagine we watched an object for some time and we kept track of how it moved each second. This is called a motion diagram. I've drawn you one here. I free-handed it so it's not terribly neat. At time 0, where were we? 0. After 1 second, where were we? Direction. East or right. After 2 seconds, where were we? After 3 seconds, where were we? So this is a motion diagram. A motion diagram is basically a series of dots connected with arrows with some kind of a distance axis underneath so you can compare how far you've traveled. We want to try and put this together in one picture. One way is we could summarize this in a table. So at time 0, we said that I was at 0 meters. Where was I after 1 second, Amber? Yep, see how to read it? Where was I after 2 seconds, Amber? Yep. And after 3 seconds? Now, I made these numbers up as nice as possible. Normally, in the real world, the numbers don't work out this evenly, but this will give us the theory. Another way we could summarize this would be in a graph. Now in science, if we're going to do a graph, every graph has to have certain properties. It has to have a title. You have to label the axes. It has to have a scale. And we're going to talk about that, but I'm just going to walk you through it right now. We are going to put time, comma, t in seconds. That's going to be on the x-axis. And we're going to put position, and the symbol for position is actually distance d. In meters on the y-axis. We're going to include a scale. Let's go with changing colors, Mr. Dewick, so it doesn't blend in. 2, 4, 6, 8, 10, 12, 14. Kenzie, you could label every single square, but I find that gets cluttered, so usually I'll label every other square. And we're going up by ones. Didn't have to go up by ones, but I did this time. And we could go 2, 4, 6, 8, 10, 12, 14. So we've labeled the axes, we put a scale. The last thing this graph needs is a title. Don't get fancy. How about graph of position versus time? There's my title. And we're going to graph these points. We're going to take this table, Curtis, and similar to what you may have been doing in Math 10, we're going to say we can translate this into a picture, into a diagram, into a graph. I'll go back to Amber again. Amber, at time 0, where were we? So this graph goes through 0, 0. Not every graph will, but this one does. After 1 second, where were we? Which one? Read from the chart. After 1 second, where were we? 2. So 1 second over, 2 meters up, like that. 1 over 2 up. After 2 seconds, where were we? After 3 seconds, where were we? See a pattern? What's the pattern, Jake? 2 up, 1 over. I think, Emily, it's fair game. If we assume that this motion continues, I think we can extend this line and make a prediction about the future. Let's assume, Jacob, that this person or this object or whatever this is continues at a uniform speed, at a constant speed, the same speed. I think it would be there, 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 and there. And we can connect them. If you have to freehand, I'll put up with it in your notes. If it's a lab, use a ruler. I'm going to use a ruler here. Like that. With me so far? We've taken a table, and Miller, we've tried to make it a picture. Why? Our brains are better at spotting visual patterns than they are at spotting numerical patterns. All right, now we're going to put our thinking caps on for a second. Suppose I traveled at twice the speed as before. Complete the new table, and we're going to graph it on the same graph. So if I'm traveling at twice the speed, well, first of all, at time 0, where am I still? If I'm traveling at twice the speed in 1 second, instead of having traveled 2 meters, how far will I have traveled? 4. 8. 12. Let's graph that. I'm going to graph that in a different color. I'll graph mine in red, just so it stands out. If you have a different color, great. If not, probably not that big a deal. This looks like this. It goes through 0, 0, 1, 4, 2, 8, 3, 12. And again, I notice a pattern, but I think this time the pattern is up 4 over 1, up 4 over 1, up 4 over 1. There'd be another point off my graph right there. It's sort of like connecting the dots, but with style.
They did this in socials, they're doing
Yeah,
climate.
they've done graphs before, but I always teach it from scratch, assuming they've forgotten it all, because teenagers. Let's be really clever. Hayden, let's call this graph A. Let's call this graph B. And Ty, here's the question. Who's traveling faster, graph A or graph B? B. Which line is steeper, graph A or graph B? So if I hear you correctly, the faster you travel, if I graph you on a position time graph, what can you tell me about the steepness of your line? Steeper? Okay, so you ready? Look up. Which is faster, this or this? How fast would this be? Think about it.
Equal.
This is stopped, not constant speed. This is stopped. On a position time graph, what this is saying is your position isn't changing. Time is moving, but your position ain't changing. You're not moving. You're staying in one spot. What would this be? Negative, going backwards, going left, going down, going south, however we want to define it. Downhill, we can say coming back to where you started from. Put the phone away. One more time, I'll hang on to it. Thank you, dear. Does that make sense? It gives us a visual way to start to compare speeds. And the basic rule we're going to say, Kenzie, is if it's steeper, it's faster. If it's shallower, it's slower. If it's horizontal, you're stopped. Oh, and then if you go downhill, the same thing but negative. So really steep downhill means you're coming back really, really fast. Really shallow downhill means you're coming back but really, really slow. Turn the page. I wrote down here. So what do you notice about these two lines? Jake already pointed it out. He said, the steeper you go, that's too much writing. You know what? How about this? Faster equals steeper. Is that okay? And flat equals stop. What's the fancy word for flat that begins with the letter H? Okay, horizontal, but I didn't feel like typing out, Dylan, the word horizontal. I'm like, flat equals stopped. Downhill equals backwards or south or down or left. All of those conventions that we talked about that could mean negative. It equals negative. However, we can be even more specific. The steepness of a line tells us on a position time graph your speed, but we can be even more specific. We can actually then calculate the speed. And you may have started learning about this in Math 10. My Block C's learned about this about half an hour ago. So I timed this on purpose this way, Amy. What do we call the steepness of a line, Amy? Begins with the letter S. Slope. And we can find it from a graph by going, do you remember, Darian? How can we find the slope? Slope is what over what? Rise over run. Keeping in mind a couple of things. Downhill is negative. Uphill is positive. Flat is 0. You can go rise over run, but if it's flat, clue in, it's 0. Oh, and in math, this won't happen in science, but in math, what's a vertical line? Undefined. And the reason is, if we bring it in terms of a speed, Brady, you can't be going more than one speed at the same time unless something's gone horribly wrong. You want a vertical line? That's I apologize, this is gruesome, but that's an explosion where body parts are going at different speeds. That's about the only, if you want a real life situation that that might graph a vertical line for a portion.
Or it could be a car crash and when parts coming off of the car.
Yeah, something's gone wrong. Let's keep our physics happy. We do look at car crashes in Physics 11, but we analyze them safely. What do we mean by the rise over the run? I wrote down here, find the slope of the following lines. You know what? Let's be clever again. How about let's call this line A. Let's call this one line B. And then let's just work our way down. Line C, line D, line E. Is that okay? And I'm going to zoom in so you guys can see a bit better. To find the slope, Emily, what you first need to do is you need to find 2 points that the line goes through. The fancy word for that, because I'm a mather, you need to find 2 lattice points. And what I mean by that is, for line A, I would not, don't write this down, I would not use that point and that point. Why wouldn't I use those 2 points? They're hanging in midair, right? Horizontally, at least, they're hanging in midair. So what I'm going to look for are 2 points. You know what? I would use that point right there and that point right there. Once you have that, you can draw what we call the slope triangle. The slope triangle looks like that. You draw a little half triangle. Do you have to draw that, Mr. Dewick? I would on a quiz or a test because it helps you count without making mistakes. I might not in my homework if I'm lazy, but certainly in a quiz or a test I would. Because, Justine, now I can count. What did we define slope as? What over what? The rise is 1, 2, 3, 4, 5. The run is 1. The slope of line A is 5 over 1. Or just plain old 5. All right, that's too much writing. Math 10s who had me today, what letter do we use for slope? M. Why not an S? Because not all math was done by English-speaking people. It's from a French or German word for mountain, slope. So I'm going to find the slope. What's the slope of line B? What's the slope of line B? Horizontal. What's the slope of line C? Okay, we need to go rise over run. I think for line C, I might pick this point and this point. Sarah, if I do that, what's my rise? What's my run? The slope of line C. Mr. Dewick. Yes, Oscar. I didn't pick those 2 points. Mr. Dewick, I picked this point and this point. Fine. If you did that, don't write this down. What's your run? 4. Sorry, what's your rise? 4. What's your run? 8. What is 4 over 8 in lowest terms? 1/2. Nice thing about finding slope with rise over run, you'll get the same answer no matter which points you use, as long as you pick points that clearly go through the grid lines. Is that okay so far? On your own, find the slope of line D. I'm going to give you one hint. It's downhill. So what is that going to mean? Nope, that's wrong, Mr. Duke. Dylan, yeah? Negative 1 over 4? Is that what you got? Pardon me? Do we ever write numbers with fractions with nothing on the top? Oh, you can put the negative on top or in front, yeah. So it's negative 1 over 4, and you can either say that as negative 1 over 4 or negative 1/4.
Oh, with the, okay.
We're good?
Sorry, yeah.
Good, try E. Try finding the slope of E. This one, oh, goes through there. Turn the page. Here's the situation. I've given you a graph. I labeled it distance from start versus the time for 2 cars. On the y-axis, we're graphing distance or position. On the x-axis, we're graphing time in seconds. Which car had a head start? I wrote down here. Label that line A. Which of those 2 cars had a head start, and how can you tell? Which one started at the 40? This one right here is car A. Okay. Pardon me? Is it supposed to be touching the line on the top? Touching the corner. I'm not sure what you mean. Give me 1 second. Let me look. Because sometimes when So, Brendan had asked us to find the slope of line A. Brendan asked a good question because he's saying, Mr. Dewick, it's tough for this line to specifically be sure of certain points. Brendan, I'm positive that this point is right. Yes? And as I walk along here, I think maybe that one. Looks pretty good. Probably because they cross right there, I think we can assume they're supposed to cross right on a grid line. So what's the slope? Now, this time when you count the squares, you need to realize vertically you're not going up by ones. What's 1 square worth vertically?
10.
So if I draw my little triangle here, my rise is 1, 2, 3. It's 4. Well, it's from 40 to 80. What's the run? 1. I don't think horizontally we're going up by 10s. What are we going up by horizontally? Each square is worth, yeah, I marked it with 2s, but what's each square worth? 1. So I think it's 40 over 5. What is 40 over 5 in lowest terms? So far, so good? Now, Jacob, really what that is that's 40 meters in 5 seconds. Right? So part C asks, what's the speed of the car A? And this is the whole point of this lesson that I've been trying to work my way towards with all the distractions and the shuffling. The speed is the slope. Dylan, what did we say the slope was in part B? No, what did we say the slope was? What answer did we get in part B? What did we write down? 8. You know what the answer for part C is? You know what the speed is? 8. The speed of a position or distance, the slope of a position time graph is the speed. The speed is the slope is 8 meters per second. That's been the whole point, Amber, of this lesson. If it's a position time graph, or Curtis, a distance time graph, and they start talking about speed, they're not really talking about speed. You know what they're talking about? A different word that begins with the letter S and rhymes with ope. Slope. Slope. So, let's see if we can handle, what's the slope of line B? Well, line B definitely starts here and goes through here. The rise is from 0 to 80. So the rise is 80 over. The run is what? 1, 2, 3, 4. Run is also 5, yes? Hey, what's 80 divided by 5? 16. What's the speed of car B? 16 meters per second. 16 meters per second. 80 divided by 5? No, I used a point at there. I know it goes through 0, 0, and I know it goes through that point there. It's 8 squares vertically, but what's each square worth? 10 vertically. It's 5 squares horizontally. Now, by the way, it doesn't go right through there. If you use that point, it's a little bit off. Trust me. It is, trust me. I did the math. It doesn't quite go right through there. It's a little bit off. Trust me. There's a reason why I jumped to that point right there, because I used a computer to graph this, so I know the equation that I typed in, and I know what it goes through. So, let's see. We are going to